Okay, hi everybody. Welcome to physics, constant velocity particle model. What I want to do here is go over some of the basics that we've been learning about all these times. And yeah, let's get started with this page. In your textbook, oh shoot, I have an old one here, so I'm not sure. But it's right after practice number 4. This is the page right after that, so you should be able to see it. And what I want to do is basically go over some of the big stuff. Okay, so CVPM kind of threw folks for a loop when we were, doing practice 4 in class today. But basically, that stands for a constant velocity particle model. And everything we've been looking at so far has been moving with constant velocity. So what we're saying here is that we can model the motion of an object moving with constant velocity. So you need to know when you want to use this and when you don't. Okay, so far everything we've done has been constant velocity. But what it means is that an object that is moving is not getting faster or slower. Right? It is moving with a constant speed. It is covering the same distance. Its position is changing constantly the same way every single time, right? That's constant velocity. And it's not that there are a ton of real life examples here. I mean, constant velocity motion is very specific, and not everything moves with constant velocity. However, when we do have something moving with constant velocity, we have several ways we can represent it. And that's what we've been working on all this time. Well, plus a few other things, right? So our visual representations include position time graphs, right? And generally, we either have arrows going up away from the axis, right, like this, or perhaps, in fact, wait, let me put an arrow on that so that if you look at it later, you'll see. Or we could have objects moving this way, downward, right? But notice my slope is constant. That tells me that that's my velocity, right? And here I have a negative velocity and here I have a positive velocity, but both of those are constant values. That's kind of the key thing. Second, oh, what color did I have here? Blue. Let's be consistent. Let's keep doing blue. We can have a velocity time graph. These took us a little bit of time to get to, and what we figured out here, like if I start with the blue, that's got a constant positive velocity, and then my red line, negative constant velocity. Look a little more like stair steps. Okay, but the same thing is happening here. We're looking at the visual representation of what is my object doing. It is changing its position at a constant rate. And so my visual representation here on my xt graph, the slope is velocity. On my vt graph, well, we haven't really defined that yet, but as you can see, the slope, because it's rise over run, it still is going to be about changing the velocity over time. And well, we're not up to that yet. Okay, we are looking for a change of 0. In this case, it's a slope of 0, which makes sense if we have a constant velocity. We should not have any change. Correct? Correct. Now, when you're looking particularly at your position time graph, we often write the equation of the line in slope-intercept form, but we change the value for y because we already know it. The m is going to be the velocity, and then x, we're measuring time. Right, so velocity is in meters per second, time is in seconds, and this b really is my initial position. Right, the b, the y-intercept here on this graph, that is where the object begins, whether it's at 0 or something close to 0 or something higher than that. Okay, so when we took this, our next representation was we took our very specific examples of our equations of the lines, which we did with the buggies at the beginning of the year, when you thought we were just messing around. And we came up with this very generic formula. Now, often this gets moved over. This expanded version, I will point out, is extra helpful when we do the colliding buggies. But often this will do the trick. If your initial position is 0, well, there is no xi, so it's really simple. It makes it really, really nice to work with. So we've got this visual representation. Oh, I went over to the edge too far. We got this visual representation. We have this visual representation. We have this representation, the equation. And then last but not least, we had a motion map. Okay, and a motion map, it's almost like putting a data table together. Right, so 0, I don't know, let's say 0 meters, 10 meters, 20 meters. And what you can do is read the points on a position time graph, and you can actually plot the dots. The key thing you have to remember here is the first time is always 0 seconds, right? This is 1 second, this is 2 seconds. Oops, I forgot the dot. There it is. Right? And what this is doing is giving me a coordinates. It's giving me a set of coordinates that I could then plot on a graph, right? 1 and 10, 2 and 20, etc., etc., etc. Right, so it's another way, and we put arrows between these. The longer the arrows, the faster the object's going because it's covering more distance in the same amount of time. The shorter the arrows are, the slower the object is. If it's at rest, our dots go on top of each other. If it turns around, I'm running out of room, so I'll just put it there. It'll go the other way. So it tells you quite a bit about the motion just by looking at the motion maps. Those are some key things that we want to take advantage of when we look at it. The last key topic that we looked at before our final third quiz, before our big test, was to look at what about area under the curve on a VT graph. And that's really another helpful thing we can calculate here. So on a VT graph, the area under the curve is the same as the displacement. When you look at a VT graph, you have no way of knowing the position. Not the initial position anyway, unless you are told more specific information. There's nothing on there for position. However, if you look at this, if you look at that, and you look at the values, like what do the axes stand for? What you'll notice if you're going to take that area, the area is going to be equal to the velocity times the time, right? Because here's the velocity, here's the time. This is why we multiply them together, we get the area. Oh my gosh, I know what that's equal to. That's equal to the change in position or the displacement. Okay, so this really helps us. Sometimes the hard part is knowing where are my boundaries. So I will point those out to you with the green marker just one last time. Okay, so one boundary is always going to be the x-axis. And then the second boundary is going to be what we call the curve, although it's really more of a straight line, right? And so then there's that one too, right? So the area bounded by that's obviously going to be a positive displacement because it's above, it's in the first quadrant and so forth. This one, when I do that math, it's not hard, but it's going to be negative because it's under the curve. It's in the fourth quadrant. That's what I want to say. It's in the fourth quadrant. So something to keep in mind. Okay, hopefully that's the big picture. So how do we actually like do this? Here's practice number 4, and maybe not. This is something that, you know, came really easily to you, but if it was anything like it looked like in class, this was a bit of a struggle in spots. So let's take a few minutes and kind of go through some of the key pieces here. All right, so first of all, right away, this threw people off. What are you talking about? Does it move? All this is asking is, does it move with constant velocity? Constant velocity particle model. The particle, does it act like it's moving with constant velocity? Can we model that motion as constant velocity? That's all we're asking. So when you look at 1, 2, and 3, look at the description. Does it move with a constant velocity? Well, number 1 says it starts from rest and reaches a speed of 8.5. Okay, so it starts with a velocity of 0, and then it has a new velocity at the end. So this one is an obvious no, because how do you go from 0 to 8.5 if you don't change? It's not even possible. Okay, number 2, they talk about traveling for 20 seconds at the speed of 8.5 meters per second. It does not appear to be changing. So yep, there you go. Number 3, driver sees a deer in the road, blah, 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 applies the brakes. Okay, we all know what happens when you apply the brakes. You slow down, and oh look, that's the second part of the question, right? So slows to a stop. You do not have the same speed throughout there. So that one is an obvious no. All right, so the only one actually doing anything with constant velocity is right here. Choose one of the problems. Oh, luckily for us, there is only one. For the problem you selected, draw at least 3 diagrams and graphs. Choose them and yeah, okay. there's really only 3, so it doesn't help us, right? To just say, oh yeah, only choose 3. There are only 3, right? And then there's our motion map. All right, so 0 meters. I'm going to go up by 10s on this one just because I'm not going to do all 20 seconds because that's insane. You'll get the idea. Okay, so if I think about this, time, position, time 0, time 1, time 2, times 3, and it goes all the way up to 20, obviously, but we're just going to stick with 1, 2, 3 to kind of keep things a little bit easier. It starts from rest. We can assume it starts from 0 position because we're not told anything else. Right, at 1 second, this is traveling at 8.5 meters per second. So after the end of 1 second, it's 8.5 meters away. Makes it simple, right? At the end of 2 seconds, it's going to be 17 meters away from the starting point. At the end of 3 seconds, it's going to be 25.5 meters away, etc., 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 all the way up to 20, right? But you get the drift. It's going like that, right? If you want to get fancy, put in your dots here, right? 1 second, 2 seconds, and you can put the values on here. But I got to be honest, this is going to get real messy real fast. It's not exactly a fine point marker I'm working with here. So 8.5 meters. This is position, and it's in meters, and there's time, and we have that in seconds. And this is in meters per second, and this is also in seconds. We should have units and labels. I've been telling you that for 3 weeks, so I should listen to my own self. All right, velocity time, nice flat line. It's a positive 8.5 meters per second. Easy peasy. Now, this motion map, thanks to my little chart over here, is pretty easy as well. So 0, it's going to be here. 1, it's going to be at 8.5, so it's somewhere around there, a little less than 10. This one's going to be a little less than 20. This one's going to be a little less than 30, and draw yourself some arrows in between. And it would keep on going in the same direction. Now, if I'd have done a better job, my arrows would be all about the same size. Let's try that. But, you know, I'm kind of eyeballing it here. So you get the idea, though. Okay, solve for any unknown quantities. This also threw many of you, right? Because, oh, excuse me, sorry, 3:30, 4 o'clock on a Friday. I'm ready for bed, people. You know, I'm a vampire. I cannot be up at night. Using the constant velocity particle model, solve for any unknown quantities. Well, what don't we know? The main thing that we didn't take the time and figure out is how far this sucker can go in 20 seconds. So let's do that, shall we? All right, xf equals vt plus xi. Where is it at the end of 20 seconds? Well, let's see. We're going 8.5 meters per second. We go for 20 seconds. My initial position is 0. That's why these equations of the line are so handy, because you can figure a whole bunch of stuff out for anything, right? For any situation. As long as you know the equation for the line, you can work with something that's way off the graph that you didn't bother with. Hopefully that makes a little bit better sense. All right, next one. Oh, this was the fun one. Oh, my graph is like off my screen here. I can't really see the whole thing. This is going to be a challenge. All right, well, I'll just have to eyeball this one, that last graph. And of course, that's the one everybody really struggled with. So nice job, Grady. That's all I can say there. Determine the change in position from t equals 2 seconds to t equals 3.5 seconds. Look at this. It's not a position time graph. It's a velocity time graph. If we want to figure out how far we are going in a time interval on a velocity time graph, we need to work with the area under the curve. So the first boundary is always your horizontal axis. So if you can't really see it too well, make a point. Make a new, like, add a little stuff in there, a little color, make it pop. All right, 2 seconds to 3.5 seconds. So you can see I'm looking for this rectangle right there. My answer is going to be negative. It's in the 4th quadrant. Don't just count the boxes. Don't tell me it's 6 because there's 6 boxes. All right, this isn't math class. Not everything counts the same. Look at what this stands for, okay? So if we want to know delta x, which is what we're looking for here, this is negative 40 centimeters per second. This is 1.5 seconds. Now you notice it's not like drawn to scale. So again, be careful. Read the axes. That's really, really important. This comes out to be negative 60 centimeters. And that works. determine the change in position from 5 to 6. Okay, so 5 to 6, from here to here, we're above the line. This will be a positive one. Again, don't just count the boxes. Don't tell me that it's 2. And don't think it's to scale, because it's not. You have to read the axes. All right, so here to here is 20. 20 centimeters per second. From here to here is 1 second. So lo and behold, I can do that math without a calculator. Look at me. All right, so 20 and negative 60. Now this last question, ooh, that's the hard one. So which means, and especially since I can't really see too well, so lucky for you, well, maybe not so much. I'm going to do my best with a luckier color than green. Green is not my favorite of the markers, but that's okay. No big deal. All right, so considering I know how high up this will go, I'm going to do my level best, 40, 60, and then 80 at the top. This is centimeters. Okay, now it says assume a position t equals 0 of 20. All right, I figure it should be lower than that. This isn't calibrated all the way. Uh-oh, uh-oh, uh-oh. Let's pause. I guess we're calibrating. Sorry, guys, I'm sorry to be recording while we calibrate. I can't find the spot to get rid of this. So I guess we record all the way through it. Come on. Okay. Now we got it. All I wanted to do was erase my dot. Man, what a touchy little thing this is, huh? That's what I get. Okay, let's try this again. Whew. It scared me a minute. I thought I broke the computer. And Mr. Hartz went home because, you know, he doesn't like to have fun on Friday afternoon recording lectures. He records them at other hours. So anyway. So my first one is, I'm going to guess like 20. Ooh, that looks a little better. I guess that calibration came in handy. All right. Now, this is what helps me. We got to figure out where this thing is all the time, right? So, all right. Let's just start with t equals 0. We know it's at 20. 1, 2, 3. Figure out where it is each time. Let's put a little more on there. All right, so t equals 1. How fast am I going? I'm going 30 centimeters per second. So in 1 second, I can go 30 centimeters. I was already at 20 centimeters, which means my new position is 50 centimeters. Right? That's good. All right, so at 2 seconds, what am I doing here? At 2 seconds, how fast am I going? I'm going, oh wait, maybe I read the wrong one. 1.5 to 2. Nope, never mind. I'm going to read it up here. All right, so at 2 seconds, I'm still going 30. So that means I'm going, my new position will be 80 because I covered another 30 centimeters in that 1 second. All right, so now I'm at 80. Now what? At 3 seconds, oh dang, I turned around. So negative 40 centimeters per second means I went backwards 40 in that 1 second. So now I'm at 40. Okay, let's plot that to start with. So 0 is at 20, then I go to 50, which is like there-ish. Oh gosh, this thing's not calibrated at all. Then we're up here at 80, you get the idea, even though it's not really in the right spot. And that's at 3, then I'm here at 40. Okay, so now what's going to happen? Well, now if you notice what's happening here is we're changing velocity again. And in fact, we're coming to rest. This means we have 0 velocity, but it's before the 4 and after the 3. So what do we do? Well, I would work with half a second here. I know it's not, even, but we'll get a better idea if I work with 3.5 seconds. And for that half a second, I'm traveling at negative 40. So that means I go backwards 20. I don't go back at the full 40 because I'm not traveling for a full second, but I am traveling back for half a second. So that gives me 20 as my 3.5 second spot. And then at 4 seconds, I'm at rest. That means I'm going to stay in the same position. And then at 5 seconds, I'm at rest. Or well, things will start to change again at 5 seconds, right? But I'm going to say I'm still at rest for a little bit there. And then at 6 seconds, well, that's when I'm traveling again at 20 meters per second. So where was I? I was at 20, So let's go up to 40 for 6 seconds here. Try it, hit it for there. It's not simple, but hopefully you see the logic. And it's not perfectly drawn here. But that should give you an idea. Of all the skills, this is the tough one, man, without a doubt. Taking a velocity time graph and coming up with a position graph is tricky stuff. I find this to be super helpful with that. So I hope that you find this a little bit helpful. I'm going to put in a plug again for all the materials that we have at the back of this unit, so that if you don't feel certain, my strong suggestion is for you to practice a little bit and then come in and check your work. And you know what? If it doesn't match, we have something to talk about, right? And it's not just an awkward conversation because you forgot to bring me coffee and a donut. So make a point of trying a few things there, and don't bring me a donut. I'm actually allergic to donuts, but I'm teasing you. So, but do come in and see me if you need some help, and bring your work, and that'll give us a starting point. It's so much easier that way. All right, you guys, I hope you have a great weekend. Talk to you later.